Hello everyone. This video is about single phase semiconverter with DC separately excited motor. Single phase semiconverter is one for one converter. Hence, with this arrangement, it is possible to obtain only 1/4 of the operation of the motor. This is the circuit of the single phase semiconverter, which consists of 2 resistors and 2 diodes. The output of the semiconverter is fed to the armature circuit of the separately excited DC motor. The field winding of the motor is fed from a constant DC source. With this arrangement, we will get the variable speed operation of the DC motor below rated speed. This is achieved by varying the output voltage of the semiconverter by changing the firing angle. There are two modes of operation of the circuit: continuous conduction mode and discontinuous conduction mode. In continuous conduction mode, the armature current is always greater than 0. When we trigger T1 during the positive off cycle, the current will flow through T1, through the armature circuit, through D1 and back to the source. Hence, the armature circuit is connected across the supply voltage Vs. At pi, D1 is reverse biased, and hence, after pi, D1 is reverse biased, and hence, D1 is turned off at pi. After which, the armature current freewheels through T1 and T2. During that time, the armature circuit is short-circuited by T1 and T2, hence the armature voltage is 0. During the negative off cycle, the T2 is triggered, and hence the current flows through T2, through armature circuit, through T2, back to the source. At 2 pi, T2 is turned off, after which the armature current freewheels through T2 and T1, hence the armature voltage is 0. The time operates in 2 intervals: duty interval and freewheeling interval. During the duty interval, the armature circuit is connected to Vs, and during the freewheeling interval, the armature is short-circuited, hence the armature voltage is 0. Since the converter is a 1/4 converter, we can get only 1/4 of operation, that is, rectification mode alone is possible. This is the waveform for the converter output. The first waveform is the source voltage waveform. The second waveform is the armature voltage waveform. And the third waveform is the armature current waveform. From alpha to pi, when T1 and D1 are in the on condition, the armature voltage is same as that of the supply voltage waveform, Vm sin omega t. Then from pi to pi plus alpha, when T1 and D2 are in conduction, that is during the freewheeling mode, the armature voltage is short-circuited, and hence the armature voltage is 0. From pi plus alpha to 2 pi, when T2 and T2 are in the on condition, the armature voltage is the mirror image of the supply voltage waveform. The armature current is given by the third waveform, which is continuous waveform, which is always greater than 0. Now the average output voltage is derived here. To derive the average output voltage, we have to integrate the armature voltage over the period alpha to pi plus alpha. Since there are 2 pulses in per cycle, we have to take 2 into alpha to pi plus alpha VAT omega t divided by 2. And substituting Va equal to Vm sin omega t, and we have the output voltage from alpha to pi. From pi to pi plus alpha, the voltage is 0. So if we integrate the Vm sin omega t with respect to omega t from alpha to pi, we will get VA equal to Vm by pi minus cos alpha, limits varying from alpha to pi. Hence, the average output voltage, which is nothing but the armature voltage, is equal to Vm by pi into 1 plus cos alpha. And the speed torque equation can be derived using this equation. Omega m is equal to VA by K minus TRA by K square. Substituting for VA as Vm by pi into 1 plus cos alpha, the omega m expression is Vm into 1 plus cos alpha by pi K minus TRA by K square. This relation gives the speed torque equation of DC separately excited motor fed by single phase semiconverter in continuous conduction mode. Next, discontinuous conduction mode. In discontinuous conduction mode, the armature current is not continuous. This happens due to the change in the speed. So the armature current will be zero for some duration. The armature current reaches zero before the next pair of devices are triggered. At alpha, T1 is triggered. The armature circuit is connected to Vs through T1 and T1. And when after pi, when T1 is turned off, the armature current will freewheel through T1 and T2 for some period until the armature current reaches zero at beta. Beta is the angle which is less than the pi plus of alpha, at which next device is triggered. From pi to beta, the armature current freewheels through T1 and T2, and the armature voltage is zero. Then, after beta to pi plus alpha, the armature current is zero, hence no device will be in the on condition, and the armature voltage will be equal to the back EMF. So the drive operates in three intervals. Duty interval, during which the armature is connected to Vs. Freewheeling interval, during which the armature is short circuited. Zero current interval, during which the armature is disconnected from Vs. During the duty interval, the armature voltage is equal to Vs during the positive half cycle, and during the negative half cycle, it is equal to mirror image of the Vs. During the freewheeling interval, the armature voltage is zero, and during the zero current interval, the armature voltage is back EMF. The waveforms for discontinuous conduction mode are given here. The armature voltage waveform, it is equal to Vs from alpha to pi during the conduction of T1 and T1, from pi to beta, during which the freewheeling mode of operation takes place, the armature voltage is zero. Then from beta to pi plus alpha, the armature voltage is equal to E. The average output voltage is derived by integrating the armature voltage from alpha to pi plus alpha. We can divide the interval into three. We can divide alpha to pi plus alpha into three intervals. Alpha to pi, during which VA is same as the input voltage waveform. Pi to beta, during which armature voltage is zero. Beta to pi plus alpha, during which VA is E. After integration and after substituting the limits, the average output voltage is equal to 1 by pi into Vm into 1 plus cos alpha plus E into pi plus alpha minus beta. The speed torque equation can be obtained from here, wherein we have to substitute VA. Substituting VA, the omega m expression is given by this one. And again, we have to substitute E is equal to K omega n. After substituting E is equal to K omega n, and after rearranging the speed expression for the DC separately excited motor during the discontinuous conduction mode is given by the equation B, where omega n is equal to 1 by K into beta minus alpha Vm into 1 plus cos alpha minus pi d RA by K square into beta minus alpha. Hence, the equation B gives the speed torque equation of DC separately excited motor fed by semiconverter in discontinuous conduction mode. Next, it's the time to derive the critical speed. Critical speed is that speed above which the discontinuous conduction occurs. In order to derive the expression for critical speed, we need to find the current expression during the duty interval as well as during the freewheeling interval. During the duty interval, the KVL equation is Vs is equal to IARA plus LA into DIA by dt plus E. The solution of the above equation is IA of omega t equal to Vm by Z sin omega t minus phi minus E by RA plus K1 into E power minus T by tau A. Here, Z is equal to impedance of the armature circuit, and we can write tan phi is equal to omega LA by RA, which is equal to omega tau A. The tau A is LA by RA, which is the time constant of the armature circuit. Also, we can write cot phi equal to 1 by omega tau A. This is the armature current waveform during the discontinuous conduction mode. And we need to find K1 using the boundary condition. At alpha, IA is 0. Hence, at alpha, IA of omega t, which is 0, equal to Vm by Z sin alpha minus phi minus E by RA plus K1 e power minus alpha by omega tau A. Solving this equation, the K1 value is E by RA minus Vm by Z sin alpha minus phi into E power alpha by omega tau A. Substituting K1 in the IA expression, the IA expression is obtained as given by this equation. Now, substituting for 1 by tau A equal to omega into cot phi and rearranging the equation, the IA of omega t can be written in this form. This is the armature current equation for duty interval that exists between alpha to pi. At omega t equal to pi, the armature current will be IA of pi equal to Vm by Z sin phi minus sin alpha minus phi e power minus pi minus alpha cot phi minus E by RA into 1 minus E power minus of pi minus alpha cot phi. This is equation 1. Now we have to consider the freewheeling interval. During the freewheeling interval, since armature circuit is disconnected from the source voltage, the KVL equation is this. The solution of this equation will be IA of omega t equal to minus E by RA plus K2 e power minus T by tau A. At omega t equal to pi, IA of pi will be equal to minus E by RA plus K2 e power minus pi by omega tau A. Hence, IA of pi will be equal to minus E by RA plus K2 into e power minus pi cot phi after substituting for omega tau A. We can now equate the equation 1, that is IA of pi of equation 1 and I of pi of equation 2, and equating 1 and 2 and simplifying, the constant K2 can be obtained as given by this equation. Substituting K2 in IA of omega t, the IA of omega t now becomes I of omega t equal to minus e by RA plus Vm by Z into sine phi e power phi cot phi minus sine alpha minus phi e power alpha cot phi plus e by RA e power alpha cot phi into e power minus t by tau a. Rearranging the above equation and substituting 1 by tau a equal to omega cot phi, we get the equation for IA of omega t as given by equation 3. Now we have to consider omega t equal to beta, at which the armature current reaches 0. During that time, the I of omega t should be equated to 0 at omega t equal to beta, and hence we obtain the equation 4. In order to find the critical speed, we have to consider the case that if beta is made equal to pi plus alpha, it is the boundary between the continuous and discontinuous conduction. So if we take beta equal to pi plus alpha, we can just avoid the discontinuous conduction mode. Hence, substituting beta equal to pi plus alpha and equating vacuum of equal to k into omega mc, where omega mc is the critical speed in the equation 4, and solving that equation, finally we will be able to get the critical speed expression omega mc, which is equal to Vm Ra by Zk into sine phi e power minus alpha cot phi minus sine alpha minus phi e power minus pi cot phi divided by 1 minus e power minus pi cot phi. This is the expression for critical speed of DC separately excited motor, which is fed by single phase semiconverter. In order to draw the overall speed torque characteristics, we need to get the no-load speed. The no-load speed is nothing but the speed at the no-load condition, which will happen when IA is equal to 0. IA equal to 0 is the case that can happen only when E is greater than or equal to Vm for alpha less than 90, and E is greater than or equal to Vm sin alpha for alpha greater than 90. So, considering these two cases, the no-load speeds are obtained as Vm naught, that is no-load speed for alpha less than 90 is obtained as Vm by k, and no-load speed for alpha greater than 90 is obtained as Vm sin alpha by k. After getting the no-load speeds, we can draw the speed torque characteristics as given by this diagram. So, in this diagram, it is found that the drive operates only in the forward moving mode. The characteristics for different values of firing angle are shown here. For alpha less than 90, the no-load speed is less than or equal to, for alpha less than or equal to 90, the no-load speed is Vm by k, and for alpha greater than 90, the no-load speed is given by this point at which the no-load speed will be equal to Vm by k into sine alpha. The characteristics for different values of alpha are shown here. This is the boundary line which divides the continuous and the discontinuous conduction. This is the overall speed torque characteristic of the DC separately excited motor fed by single phase semiconverter. And this waveform shows the characteristics of both continuous and discontinuous mode of operation of the converter. With this arrangement, we will be able to get only the one quadrant, that is forward mode of operation of the motor. Thank you.